Thank you. Thank you very much for inviting me. It's a great pleasure to be here today. I have enjoyed very much the conference so far, and it has shown me actually there are so many different avenues. So just let me introduce myself. I'm an astronomer at the University of Patras. My research is on theoretical and computational astrophysics. So actually I come from the astronomy side. And actually what I'm trying to do, I'm trying to explore the universe inside a computer or some aspects of the universe. Now, the reason actually I feel that I am here, and I think this is important, is that the fact that we can do active research through computers on astronomy and astrophysics, this allows us essentially to explore and not limit disabled people from exploring the universe. So actually, what comes in mind when one thinks of astronomy? I think that this picture is the most characteristic one. You think of someone, a child or whoever, looking the sky through a telescope. Now, this is all very exciting, and probably most of us that have been interested in astronomy at some point, we have been through this stage, but astronomy research at the moment is not being made this way. So first of all, if you think of astronomy and people with disabilities, especially in the sense of limited mobility, you can think of the late Professor Stephen Hawking, right? Whose disability has not prevented him from deciphering some of the secrets of the universe. So actually, one can see that it is possible and it is feasible to do research, essentially active research and very advanced despite any disabilities. So actually, let's think a bit about the interest of people in astronomy, right? Essentially how it starts. Usually it starts with curiosity about the night sky, right? You think of the day sky, I mean, you see the sun and that's it. But the night sky is so much more exciting, right? You see the stars, the sky is threaded with the stars. These are different, they come in patterns. And this curiosity can go even further if we use through binoculars or a telescope. So actually, in some sense, we actually see very few things with just our own eyes compared to what is out there in the sky. So in some sense, what is really on the sky is much more than what we can decipher, that what we receive. And we need binoculars, telescope, and other visual things. I think it was mentioned in one of the presentations these days in the conference that we only see a tiny part of the electromagnetic spectrum. And in reality, our eyes are not sensitive, our senses are not sensitive to the rest. And this is what happens with telescopes and binoculars. So if one is a little bit more advanced, they can go and take pictures of the sky. And this is a good starting point. This is one getting into the level of an amateur astronomer or an advanced astronomer. Of course, how it can go, one can study and understand the universe, right? There is the degrees in physics and mathematics or engineering that they can have applications in our understanding the universe. And this can go even to more fundamental level, essentially by applying the laws of physics into the observation. So as we will see in a little bit, in a few slides later, we will see how this connection can be made. But in reality, you think you see all the scientists, one of them is holding a telescope, but quite a few of them are essentially doing some calculations and they try to get information from the telescope and see what it really means. How far can we get with astronomy? You can even think of Isaac Newton depicted here watching the famous apple falling down the apple tree. Essentially, what we do and what one can do is to confirm or even discover the laws of physics, right? In the case of Newton, his passion and his determination to understand and explain the motion of the planets led to the discovery of the law of universal attraction, but also to the development of new areas in mathematics that were used for the solution of these equations. Now let's come to a recent result and see how computers can help us to decipher this information. So here, what we have is the black hole image, one of the big results of 2019. What you see in the big picture is an elliptical galaxy. This is a very big galaxy. It's called M87. And if you are familiar with telescopes, you may have seen it as a blob on the sky. You can't really see anything with naked eye. Now, about 100 years ago, it has been possible by an American astronomer to understand that there is over here a jet. So you see this elongated structure, zoom into this picture here, and you see that there is this blob of gas that seems to come out of something, which is over here. And back in 2019, there was the famous observation of the black hole. Now, if we look closer, we have the black hole image. So essentially, it's the event horizon of the black hole, and probably we're looking down the jet. So it's like looking down the barrel. And this structure is related to the gas that is surrounding the jet. Now, the big question is, how do we actually know these things? And essentially, I have shown you, right, a picture of a dark patch and something orange around it. And I'm telling you that this is the horizon of a black hole. And essentially, we trust the researchers who did the work, and probably you trust me. But actually, how do we really know what is happening there? And while for the first objects it would have been possible, like it was outlined at the very beginning, that the fact that we see, let's say, of this day, that we see phases on Venus is telling us that the Earth is not the center of the solar system, right? It's not what rotates around Earth. Now, this picture, from the point that we receive this image until we understand what it is happening down there, there are some more steps to be taken. And if we think of how we can decipher what is hidden in these spectacular images, we need to go and follow a few of the steps in modern research. So all the information in the picture is just numbers. Right, so there are some numbers that tell us the intensity of the light, and then the different colors that you see here as waves, red, orange, yellow, and so on, or even outside the visual band, they are essentially numbers like the numbers that are related to the wavelength. Now, what happens then is that this information, which is taken in the form of numbers, is analyzed by computer programs. So what researchers do is that they are analyzing the information through computer programs. They use some kinds of equations, but then in order to understand what is really happening, and this is the big progress of the late 20th century, is that we can also use computer simulations. So actually we have the laws of physics in the form of equations. And what we do is that we solve these equations, describe the laws of physics, and then we produce images. And then we try to compare what we see through the telescopes against these images. If there is a good agreement, then we have a possible explanation. So coming back to the example of the supermassive black hole horizon that was seen in M87, what actually this research, how this research was possible by doing an enormous number of numerical simulations integrating is the technical term for solving the equations. And after the solution of these equations, they got synthetic images and they tried to see which ones are matching better the observed data. From this information, it has been possible, after making this huge library of simulations, it has been possible to compare the simulation to the actual picture in very sophisticated ways, and then get a feeling of how big the black hole is there, how it is spinning, and what happens to the gas. So I'm going to show you now some piece of research that we have made with computer simulations with a collaborator from the University of Leeds in England, Sergei Komisarov. And what we had in mind is that we tried to understand why astrophysical jets are very bright near the point of the black hole. So essentially what we see here is the region near the black hole at the center of a galaxy. And we see two jets, two lobes that come in opposite directions. How these jets form is a very interesting question and area of active research. Now, what we were interested in is to understand why the jet has this particular shape, essentially is bright in this region, and then it becomes less bright and more turbulent. So we decided to guess, in some sense, the initial conditions. So guess what the jet is going, how the jet propagates, and then put in the right physics in the form of equations inside a computer program, integrate it, and see what happens. So essentially now I'm showing just half part of this jet. The gas in the jet moves this way. So down here, you can see it, there is a black hole, and then the material gets accelerated in this region. It goes up to the top right of the picture. I'm showing the density. And as time goes on, what one can get is that the jet remains more or less intact near the black hole. But once we go to further, to distances further from the black hole, the jet becomes very turbulent. Now, just to give a hint of what a black hole is, which deserves a discussion in its own, but I think I shouldn't deviate that far. It's a very dense object that is actually so dense that gravity makes it that strong that light cannot escape. Now, despite the fact that light cannot escape, it can accelerate the material that is trying to fall onto the black hole and produce a jet. The thing that we see in these pictures is the jet that is produced by the material that goes around the black hole through some complicated mechanisms. So actually, this is the picture. This is a still of the black of the jet that we have published. But essentially, this piece of research was addressing the question of how a jet forms. Now, I will just then try to outline the main path that we are taking, or actually, I think it's more of a loop rather than a path. We have the observables, we have the light, the particles, or gravitational waves that are a recent kind of observation that has the recent type of observation that has been possible. We obtain through these things that we observe, so that we see through our telescope, the physical properties of the system. This could be the temperature, the density, or the chemical composition. We use this as input in the equations that are describing the system. And then we try to solve these equations. Now, from the solution of the equations, we extract the physical properties in the observables, and we try to compare them against the observables that we have seen at the first place. If there is a good agreement, then there is a sign, there is a clear indication that we understand what is happening there. Now, this is obviously advanced research, and I'm not saying that this is something one can do at home, but thinking of people with limited mobility, I was thinking, and after discussing with Andreas, of what one person can do from home with just a computer. So coming back to the original question of the conference, the topic of the conference is that if someone has access to a computer, but they are some kind of keen amateur, or they are interested in something just going beyond the point of reading the news or reading books about astronomy, is there something that they can do and actually come closer to active research? One part could be some numerical simulation. So actually this would be something that a person who's either a keen amateur or someone with a science or an engineering background can handle. And to be honest, things have improved a lot from the good old days. So those of you that you have heard of some of computing, and this was actually one of the reactions of my advisors, of my research advisors early in my career, is that computing is, in a postdoc, he told me that computing is an art in itself, and it's really hard to tackle it. I'm not saying that it's hard. I'm saying that today there are some tools that prevent you from writing these strange and tricky computer programs that people had to write several years ago, but actually one could use just some software, input the right equations, and to do the simulations. So I would like to present the Daedalus project, which is something that I have used for my research, and we have used it with one of my students for research, that helps someone to solve numerically a problem, so solve a problem, a physical problem in the computer, without the need of writing the entire computer program themselves. So this is an open source program. It has been used for research, so this is one of their problems they have in their galleries. It's showing a sphere that is hot, and it has what we call convection. So it's hot and essentially it boils, but at the same time, hot material comes from the top and cold material goes to the bottom, but at the same time, it's rotating. So imagine that you have a sphere that is boiling and at the same time is stirred. So while it's spinning slowly, you don't get much effect on this boiling, but once it spins fast, you start getting these colder regions here in blue, lower pressure actually, and these red regions here that are regions with higher pressure. Now, what we have done, and that was impressive, that it required very small amount of programming. I'm not going to show you the actual numerical code that we inputted here because I will run out of time, but I will show you the result. So what we had in mind with one of my students is, without bothering of writing an entire simulation, we wanted to understand how an astrophysical disk, which is what I'm showing here in red, will evolve if you place it inside some material that is not moving, which I'm showing here in red. So this is what Maria Skirla did for her undergraduate thesis project at the University of Patras. And what we actually see is that as this object rotates, it starts forming these whirlpools, and by forming these whirlpools, you get an understanding of the physics. I will not go into the details of the physics because I don't think it's relevant, but what I'm saying here is that it was just a matter of typing a few lines that were involving the equations that we had in mind to describe a disk. This is something someone with a degree in physics or in mathematics can do, or even a very keen high school student, I believe, can do that. And then one can see that this disk evolved into this spiral because of these instabilities. Now, what happens, and are there any options if someone is interested in getting involved with astronomy just with a computer, even if they don't like programming? I think there is some great opportunities, and I will walk you through a very nice project that has been developed over the last 13 years that has actually used people powered research, as they call it, for big projects. So just allow me to give a little bit of background. Big collections of stars are galaxies. So we live in one of these galaxies in the universe. They can have tens of billions of stars, and these galaxies are not all the same. These galaxies can have different shapes and different properties, but essentially, as it was understood about 100 years ago by Hubble, they come in three main types. The first one is the spiral galaxies, which is what whirlpool-like galaxies are. Essentially, our own galaxy is a spiral galaxy. There are galaxies that look like rugby balls. They are called ellipticals, and irregular galaxies whose shape is not either whirlpool or whirlpool-like or rugby ball-like. Now, the question is, how do you tell if a galaxy is one of one shape or the other? And this is obviously not a very hard question. When the early astronomers were doing that, they had observations of a few galaxies. You can see with a telescope these kind of galaxies, and you can get a feeling whether the galaxy is spiral, elliptical, or irregular. But what happened over the last 20 years, 20 or 30 years, is that the problem that we had is that there were some surveys that accumulated an enormous amount of data. So there were some telescopes that were taking pictures of the sky in different places, and they were having information that couldn't be processed or analyzed easily. So the first thing that researchers tried to do was to, obviously, it would be a waste of resources if they were trying to look at 1 million pictures just by eyes, one after the other, was to make some computer programs that would recognize things. So they would recognize whether a galaxy is an elliptical or a spiral or an irregular and so on. The thing was that the computers were not that good at recognizing things. They were okay, but a human being is much better at this pattern recognition. So for instance, you can tell immediately that this galaxy is irregular, whereas this galaxy in the right-hand side is elliptical. Now, while the computer could recognize these outstanding cases that were clear, some pictures with subtle difference were not as easily understood by the computers. So a group of astronomers with the key people based in Oxford thought of the Galaxy Zoo project. So the idea was to make this data, these pictures, publicly available, and then people could just register in their website and then say whether the galaxies are elliptical or spiral. There was a small tutorial that was saying that this is what a spiral galaxy looks like, this is what an elliptical galaxy looks like, and so on. And then they were shown pictures that were saying whether the galaxies were elliptical or spiral. They went on to some more subtle differences, whether the galaxy was rotating clockwise or anti-clockwise, which is something that is much harder for a computer to capture. And also they were asking to classify whether this object, because sometimes the picture was not showing a galaxy, for instance, here it was showing a star or even a satellite trail, and they were the people were able to tell whether they were seeing something that was a star or a satellite trail. So by having these collections of images, more than 1 million, they formed this Galaxy Zoo, and people were registering, and then they were analyzing this picture. Now, what I have been considering is that this piece of research led to 67 scientific papers. So 67 research papers, this is a very big number. There were more than 100,000 volunteers involved. This project was not deliberately or designed on purpose for people with limited mobility, but obviously one can get involved into this kind of project. And this was their first research paper of the Galaxy Zoo project. Now, this idea evolved. It evolved to the Zooniverse project. And essentially, they had what they call people-powered research. So this could go from arts, biology, climate, history, language, literature, medicine, literally everything that you can have in mind. So for instance, in language, they have some manuscripts that one can recognize and see what the script looks like. There are other projects that are related to recognizing things. And the important thing is that they are not relying on a few people doing a lot of classifications. For instance, in the astronomy project, they had on average about 100 images classified per user. So this means that a person wouldn't get bored, or maybe they would get bored after classifying 100 images, then try another project or do something different. But actually the thing was that this was very helpful for research, and at the same time, it was a perfect way to communicate research to the public. The other important feature here is that one could build a project. So for instance, researchers that need some human assistance, provided that the task is not that complicated, so it's like comparing pictures, they could propose their own project and use it from and ask for help. In the field of astronomy, there are still quite a few projects. There are the family of the Galaxy Zoo project. In this case, it's related to the radio galaxy. So these are galaxies that are seen in radio pictures, and they have jets like the ones that I have shown you at the beginning. There are ones that are related to their spiral structure. It's even accessible through mobile phones. This could be related to mapping historic skies or about the fourth planet, right, Mars, and the geography of Mars. So actually, these are things that the human eye can do better. The problem is that having researchers or one researcher doing this for the entire time is a waste of resources, because the task is a little bit, after some point, after 100 or 200 images, is a little bit repetitive. But then if you disseminate this to the public and you ask for public help, then you can split a big project into a lot of people, and they can help with that. So is it possible to do astronomy just using your computer? I think yes. Obviously, what I believe I'm suggesting here is that one doesn't have to travel to dark skies to do astronomy, and they don't need to do that to do astronomy actively, not just by following the news or reading. There is nothing bad about following the news or reading, but I think there is much more that one can do in this direction. People that are keen on programming, there are ways of doing that, like open source computer packages like Daedalus that I have shown you before. This could be, this would require some understanding of mathematics and physics at the level of a science or an engineering degree. Yet I think that if one can do astronomy just using their computer, I think that people could even outperform their own computer and contribute to the classification of objects. So essentially, not only one can do research using their computer, I think they can do better than their computer. So at this point, I would like to thank you again for your attention, and I'll stop here. Thank you very much.